Good afternoon, everyone, and welcome to our webinar. Thank you for joining us this afternoon. My name is Jumana Tariq Abdurrazik. I'm studying for a master's degree in petroleum engineering at University of Houston, and I will be your moderator this afternoon. Today, we're pleased to welcome Aktham Shoukry, a very special guest, a PhD student from the Department of Petroleum Engineering at University of Wyoming. He received his bachelor's degree in petroleum engineering from Cairo University in the year 2014. And got hired shortly after as a production engineer in the Gulf of Suez Petroleum Company, GUPCO. Being an honors student, he was automatically hired as a teaching assistant at both Cairo University and American University in Cairo, AUC. After 4 years of experience and hard work, he got his master's degree in petroleum engineering in the year 2018 from Cairo University. Then shortly after, he started his PhD in petroleum engineering at University of Wyoming in the year 2019. His current PhD work is mainly about pore-scale events of fracture matrix injections during two-phase flow. He has 3 publications as of now, 2 journal papers, and 1 conference paper. Since his master's degree thesis was mainly about asphaltene behavior, today he will be sharing with us his highly enlightening study about the improved Cubic-EOS solid model to predict asphaltenes precipitation behavior. Please feel free to send your questions in the chat box and we will answer as many questions as possible. With that, this session will be recorded and uploaded to our YouTube channel, PioPetro. If you haven't already, please make sure to check out our YouTube channel and join our Facebook page, PioPetro, for the latest updates on our upcoming courses. With that, I ask you to give your full attention to our very honorable guest. Please welcome Aktham Shoukry. Hi, Aktham. Thank you for joining us today. We're so glad to have you on PioPetro.
Thank you, Jumana, for this amazing introduction, actually. Good morning, everyone, if you're in the US, and good evening if you're in the Middle East. Thank you for joining my presentation today. I'm going to be talking about asphaltenes phase behavior modeling, specifically to enhance my work in enhancing the cubic equation of state solid model. We're going to shed the light on a lot of stuff related to 2-phase and 3-phase flash calculations and equation of state calculations in general, the procedures, and of course, we're going to start with why we are studying asphaltenes in the oil and gas industry. So without further ado, this is just, of course, Jumana did all of that. This is just, again, an introduction about myself. I'm currently a PhD student in petroleum engineering, UW, University of Wyoming. This is my 4th year. I got my master's science degree in petroleum engineering, Cairo University in 2018. And previous to that, I got my Bachelor of Science degree in the same major, of course, petroleum engineering in Cairo University 2014. Again, I'm an assistant lecturer, currently an assistant lecturer at Cairo University and American University in Cairo, of course, doing my PhD now. So hopefully, after successfully getting the degree, I'm gonna get back as a doctor or a lecturer. And then this is just one piece of information. I like to participate in events and SP-related events and so on and so forth. So I was a paper contest participant for SPE in 2014 as a bachelor participant and 2018 as a master's participant, and I won the EAGE European Association of Geophysicists and Engineers contest that was held in Egypt in 2014. It was about low salinity water flooding modeling. So let's get started to the outline of the presentation today. We have kind of a busy agenda. So we're going to start with the introduction, and then we're going to walk through the asphaltenes properties and characteristics, phase behavior of asphaltenes, what are the lab experiments, the PVT lab experiments that we do to kind of quantify this phase behavior of asphaltenes. the different modeling approaches, and then we're going to spend some time actually in the core of the presentation, which is the equation state and two-phase flash calculations. Then we're going to move through the model that we're going to talk about today, which is concerned with the solid modeling and three-phase flash calculations for Asphaltenes phase behavior. We're going to see some samples. By samples, I mean already done tests on oil or different oil samples, and how does the model quantify the actual data of the samples. And then, of course, we're going to finish up with the conclusions and recommendations for the model. And of course, if somebody has any question, feel free to post it through. So we know that the oil prices, I mean, at least back then at around 2018, 2019, it was kind of fluctuating in the lower end, kind of. Now, thankfully, it's a little bit higher. Around $100 per barrel, I think, but back then it was fluctuating, and even now on the high end, still fluctuating relatively. So it's crucial to avoid any production problems, because if you have a production problem, then of course your production will decrease, and this will affect, especially if you have or at the era of low oil or lower oil prices, it will affect the revenue of the project. And one of the most extreme production problems are flow assurance problems. This is because it directly obstacles the oil production, reduce it, or stop it. Actually, can even reach the stage to stop the oil production, and this becomes even more challenging during EOR processes, as we're gonna see later. When we talk about flow assurance, actually a lot of problems belong to this kind of broad title, but we're talking about precipitate. So for example, if you have emulsions forming at the places that you do not want emulsions from, this is a flow assurance problem. If you have a corrosion and erosion, this is a flow assurance problem. This is something that prevents production, either due to safety, due to other damages, or stuff like that. But today we're talking about precipitates, or stuff that precipitates in the whatever the scale that you're looking at, or the or the location that you're looking at the reservoir, or for example in these images that you see in the wells or the pipelines or tubulars. Precipitates can be waxes, hydrates, scales related salt and stuff, and asphaltenes, which is our topic today. So asphaltene precipitation, and by the way, when I say asphaltene, this is it can be plural asphaltenes, or asphaltene as a group of of these different asphaltenes, because we're going to see later that asphaltene is not actually one single molecule or one single entity that you can just relate to. It's actually a group of molecules and a group of compounds. So asphaltene precipitation or deposition can actually occur anywhere, starting from upstream, from the very far upstream to the very far downstream. So it can occur in the reservoir, perforations, the wells, the chokes, the flow lines, even the transmission lines, even the refinery plants are not perfectly safe from asphaltene's precipitation or deposition. And the cost of inhibiting or cleaning these deposition problems is very high, and it's if you expect something like this to happen, of course you try to prevent it from the beginning. But if it happened, or if it's a done deal, you have to put it in the cost avenue analysis of the project. This is just an example, roughly you can spend around from 31,000 to 46,000 per well, of course, yearly, on just the chemicals of inhibiting so that you don't have any asphaltene precipitation. So it's actually a very high and costly, very high cost process to inhibit asphaltene's precipitation and or deposition. So let's talk more about asphaltenes. Like, what is asphaltenes? You know, what are we talking about here? So asphaltenes is actually a fraction of 4 fractions called Serra fractions. So asphaltenes, if you look at the table on the left, like these fractions are like ordered in a way such that it goes from the simple, you know, light zero polar compound to the most heavy, to the most polar, to the most complex in structure compounds. So the saturates, for example, are the single bonds. They have zero polarity. Aromatics, aromatics like multiple benzene rings and stuff like that. Resins are more polar, more complex. And they have like heteroatoms, and what I mean by heteroatoms is like atoms that are not carbon and hydrogen, like nitrogen, sulfur, oxygen, you know, this type of atoms. And of course, for the asphaltenes, it's the most polar, most complex, highly condensed, you know, structure of atoms. As you can see here, let me just do the pointer. So as you can see here, like this is the most complex molecular structure of them all is the asphaltenes. Some people or a different type of categorization of the fractions of, you know, the crude oil it's called PNA, which is paraffins, naphthens, aromatics. And in this case, the asphaltenes will belong to the aromatics, even though the aromatics are, the definition of the aromatics do not contain, you know, multiple ring types and, complex structures. But for the PNA categorization, it actually contains like they put into it, or it's like the different or complex structures belong into this fraction here for the PNA, so that asphaltenes can belong here. Of course, the Serra fractions are more common than the PNA. And as you see in the image here, it actually gets, you see, like if you want to, all of this are extracted from the crude oil. So you have the saturate, which is the least heavy, it's almost like colorless. Then, you know, you get more color, and then all turns to black at the end for the asphaltenes. The way they separate the asphaltenes from the, you know, from the crude oil is basically by adding alkanes in general, because as we said here, the asphaltenes are highly aromatic. So they only dissolve, or not only, I mean, they better dissolve in aromatic solvents like toluene, and they less dissolve in aliphatic solvents like, you know, N-alkanes, N-heptane, N-decane, and so on and so forth. So basically, they add like N-heptane or N-decane or N-pentane, and they follow this kind of, tree till they reach the asphaltenes. Of course, they anything that precipitates here is solids. We call it solids, and then we add toluene. We know that the asphaltenes will dissolve in toluene, so anything that dissolves in toluene will be asphaltenes, and any other non-dissolvable in toluene will be non-asphaltenic solids. And there is actually a standard of doing this, like this title that you see on the right, like IP 143 or ASTM, this number. IP is Institute of Petroleum, and ASTM is like American Society of Testing and Material. They have standards of the procedure, actually, how to extract asphaltenes, either heptane insolubles, or pentane insolubles, or decane insolubles in crude oil or from crude oil and petroleum products. So this process is actually standardized somehow. And then you reach this kind of I will say analysis or report. Almost now in every new PVT report of a crude oil, you have this Serra analysis, which is based on the procedure which we talked about before. You have like the weight percent of the saturates, aromatics, resins, and asphaltenes as a weight percent from the crude oil. And we're going to see how this kind of fractionation impacts the modeling of the asphaltenes behavior later. So what are the properties of asphaltenes? Generally, they are, when they extract them, and actually I'm working on a project, on a separate project now here related to asphaltenes. You can see that they're actually, like black powder, just, black friable, particles like this. This is, of course, extracted heptane from Gibbs crude oil. Density of these particles is around 1.2 gram per cc, so it's heavier than water. The particle range or sizes of the particles are from 3 to 6.5 nanometer. However, we're going to see how the different structures actually have different sizes. So this is just, a solid kind of, a rough kind of range of the sizes of particles of asphaltenes. The molecular structure is, as we said, is very complex, and because it does not have a single molecular structure, it's always like polydiverse, and this kind of, it has a lot. It's a mixture of structures. So these molecules actually dictate the molecular weight. So like it can go from several hundreds to several thousands units. However, based on the literature that even at least from the modeling side of view, the molecular weight, the common molecular weight is range is between 500 and 1,000 units. You can see here the different structure. Like this is one hypothetical molecular structure that was hypothesized by these here, and this is another molecular structure. Actually from one of UW's group who graduated. And you can see like, first of all, the heteroatoms, the nitrogen, the sulfur, the oxygen, and you can see that it can be different. So there is no single asphaltene molecule kind of structure that we can point to. Finally, related to the structure, as I said, there is a very famous model called Yen-Mollins model, that describes the structure of asphaltenes in terms of how they aggregate or how they group together, kind of. So if you have a molecule, the molecule is around 1.5 nanometer in size, and then at the right conditions, these molecules will aggregate. So if you have 6 molecules, you will form what's called nano aggregate. Which is around 2 nanometers. So these molecules will kind of condense and aggregate in a way that they will form a structure or nano aggregate structure of size 2 nanometers. And of course, because you can see they aggregate, we expect that the density of nano aggregates is higher than the density of the molecule. And if you have 8 nano aggregates, again at the right conditions, they will further aggregate or flocculate to form a cluster, which is around 5 nanometer. And again, the density of the clusters is much higher than the nano aggregates, which is much higher, of course, than the molecule. These kind of structures really affect the position kind of gradient in the reservoir, or especially in the reservoir when you when you have an asphaltene layer, how much the concentration is varying versus depth. You have to know which kind of structure you expect, so that you can account for the correct density and then account for the correct gradient, of the asphaltenes. I strongly recommend Oliver Mullins' papers. He has a lot of papers. For me, he's the godfather of asphaltenes, or asphaltene science. He has a lot of papers concerning this kind of topic. So related, or when we talk about stability actually happens in a kind of a stepwise approach. So again, you have a molecule of asphaltenes, and then if it gets, let's say, little bit unstable, these molecules tend to aggregate. You have different molecules, you have numerous species of asphaltenes, and by species of asphaltenes, I mean like later we will see that asphaltenes are actually different species. You have interfacial asphaltenes, which are asphaltenes that is responsible for the lowering or higher the IFT of the crude oil and stuff like that. So you have different species of asphaltenes aggregate, and then when they reach a level of instability, they precipitate. And what I mean by precipitate is like they form a different phase from the crude oil. So they separate into the solid phase from the crude oil. And then less and less instability, these solids will flocculate or aggregate. It's kind of the same meaning. They will gather up together, and then the most kind of unstable is that these flocculated solid asphaltenes will deposit or absorb to whatever solid it's around. They either will do the clogging of walls, or if they're in the reservoir, they will do wettability alteration, because the adherence of these asphaltene molecules, it will become from water wet to less water wet or more oil wet scenario on the pores. Today we're concerned, as you can see, like there are a lot of phases happening in the instability of asphaltenes, and there are a lot of each phase has its own kind of models, its own concepts and principles. Today we're concerned about the precipitation phase, which is just getting the solid phase of asphaltenes separated from the liquid phase of the crude oil. So we're in this phase here right now. So for the precipitation phase stability, there are 2 points of view related to how the asphaltenes get precipitated into the solid phase. The first point of view says that, okay, asphaltenes, as we know, are highly polar, so they tend to attract to each other. However, the resins kind of cover up or wrap up the asphaltene structures and prevent this attraction due to sterile repulsion, between resins to happen. And if there's a certain condition somehow that will remove these resins from the walls of from the outer walls of the asphaltene, so that it becomes kind of bare naked, these structures, and the attraction, of course, will kind of counter, or I would say overvalue or outvalue the resins that were removed. So these asphaltenes will join forces or join structures each other, and when they join, they will separate due to the density out of the crude oil into the solid phase. So it's basically a colloidal kind of explanation of the instability of asphaltenes, and we got it's related to the it treats asphaltenes as colloids, surrounded by other structures, and if these structures are gone, then these colloids will precipitate. So it's a kind of a physical point of view of asphaltene stability. Okay, I see a question here. I don't know if shall we go and then answer the question in the end, or is it better to answer each question, as soon as it gets posted? Let me go through, the presentation, and then I will try to get back to the questions, so that I can answer all the questions at the end of the presentation. Of course, hopefully, you don't, as the audience, you don't mind that. So the second point of view of precipitation instability is actually a solubility point of view. It's like, as you can see, it's just like methane, for example. You know that some of the methane, or let's say at higher, high pressure, high temperature, crude oil does have methane in its composition, you know. But then when you change the conditions of pressure and temperature, this methane gets out as a gas phase. Typically, they say it happens to the asphaltenes, but instead of getting out as a gas phase, it gets out as a solid phase. So basically, what happens is that if you have conditions that will disrupt the solubility of the asphaltene as a component or asphaltenes as a component from the crude oil, the group of asphaltenes or some of it will precipitate or get out of the crude oil phase in the solid phase. And this approach is the more common or more common than the colloidal approach or the, you know, kind of physical practical kind of approach, as we're going to see in the modeling approach and the modeling different models. There are actually more solubility models than colloidal models. So the second point of view is more common or more commonly accepted than the first point of view. Also, we have a publication of one of our esteemed professor in UW, Dr. Gwal, Dr. Lamia Gwal, who in her paper proved that the resins, the resins removal of asphaltene, like the resins kind of separation, does not affect the asphaltenes, you know, precipitation or asphaltene instability in general. So this actually kind of directs our attention to the second point of view more than the first point of view. Since we're talking about a new phase, then we know that a new phase means a new phase envelope in the PT diagram, you know. So this diagram is called asphaltene precipitation behavior, asphaltene precipitation envelope. I'm sorry. This is one of the most important, diagrams or plots for the asphaltene phase behavior, because it basically explains it literally explains the phase behavior of asphaltenes. So we have this vapor liquid bubble point curve. Of course, if you zoom out a little bit, you will see that the vapor liquid bubble point, you will see the critical point on the right here. You will see, the dew point curve, continuation. But for the asphaltenes, we just kind of zoom into the vapor liquid bubble point. So the asphaltene phase envelope occurs at the vapor liquid bubble point curve. So the asphaltene phase envelope basically consists of two curves. Like similar to the two phase, the vapor liquid consists of, bubble point and dew point. Here we have something similar. We have the upper envelope and the lower asphaltene envelope line, or lower asphaltene envelope curve. Any point on the upper asphaltene envelope, we call it AOP, or asphaltene onset pressure. And when I say the word onset means the condition at which the precipitation is starting to happen. So I can say onset pressure, I can say onset temperature, I can say onset composition or onset solvent, as we're going to see later. So the word onset means the condition at which it starts to precipitate. In this case, we're talking about pressure, so it's asphaltene onset pressure. So at this temperature, this is the value of the pressure at which asphaltenes will start to precipitate, and so on and so forth. And of course, the lower is the vice versa. It's like the asphaltenes will start to precipitate if you're increasing pressure, but if you're decreasing, it's actually asphaltenes try to start to vanish, at these points here. Some references call this envelope as upper AOP, so UAOP, and some references call the lower one as the offset pressure, like the opposite of onset, basically here you have only liquid, and then here you have liquid and asphaltenes, and of course when you hit the vapor liquid, you have liquid, vapor, and asphaltenes, and here you have only liquid and vapor. So this is this envelope is explains the phase behavior of asphaltenes in terms of the PT diagram. So what is the effect of pressure if we return here? Like, let's say we have constant temperature, like constant x-axis, and then we're increasing the pressure. You see, first of course, like we don't have any asphaltenes, and then when we hit the AOP, asphaltene starts to form, increase, and then reach the maximum at the, at the vapor liquid bubble point curve, and then decrease again till they vanish at the lower AOP. So basically this curve, you see AOP increase, the saturation point, which is the bubble point, and then decrease back to the lower AOP. So this is the effect of pressure. For the composition, let's say, imagine like you're adding different solvents to the crude oil. The precipitates of, or like how much of asphaltenes are precipitated depends, of course, on the solvent you're adding. And as like the heavier this solvent, the less asphaltenes precipitated you will have. Because as we know, asphaltenes are heavy, so they prefer to solve in heavy solvents than in light solvents. So for example, if you have like here butane, pentane, hexane, heptane, octane, and decane, you will see that the precipitates percentage decreases as you make the solvent heavier in this case. One thing I want to say is that there is no physical relation between asphaltene stability and the oil API. So one can say, okay, if I have an oil API that is high, I should, like have high grading, I should expect that I won't have a problem with asphaltenes, because asphaltenes are heavy, and I cannot, since the API is high, this means that I have less asphaltenes, because if I have more asphaltenes, then it will make my crude oil heavier, and then I will have lower API. But actually it's kind of the other way around, because if you have a higher API crude, then we know that we have small asphaltene content because it's a higher API. But because this crude oil, the surrounding environment of the asphaltene is higher API, this means that it is kind of a light solvent. So asphaltenes is actually less stable because the surrounding grading of the crude oil is actually lighter. So even if you have a small amount of asphaltene, you expect it to precipitate kind of faster than if you have a lower grade of API. Even though the lower grade of API or the heavier crude oils will have higher amount of asphaltene. This is again related to the what is the crude oil that is dissolving asphaltene? Is it heavy? If it's heavy, then probably I won't have any problem. If it's light, then any change in conditions might trigger the precipitation of asphaltenes because the crude oil is surrounding the asphaltenes is actually lighter. So I just want to point this out, and we're gonna see in the you reach the oil samples testing that actually some samples have very low amount of asphaltenes, yet they have higher precipitation tendencies than the higher or the heavier crude oils. So what are the asphaltenes PVT experiments that conduct in a PVT lab? Of course, you can measure the asphaltene onset pressure. So you can, at different temperature, you can reduce the pressure, step by step. And there are a lot of methods that you can use to measure AOP. Unfortunately, it's outside the scope of the presentation, but I can briefly talk about them. You can, like, imagine you have a crude oil, and then you are at constant temperature, and you're reducing the pressure. How are you going to detect the formation of asphaltenes? You can detect it by light. You can detect it, absorption basically of the light. When you have asphaltene, you have more absorption of the light than if you don't have asphaltenes. So any kind of inflection point of the light absorption, this means that at this pressure, asphaltenes were formed. You can detect it by viscosity. You can detect it by density. Any kind of before and after change of behavior, then you can detect the AOP basically. Another PVT experiment, which is very common, is how much precipitate you get by pressure. So, if you remember this curve, this is of course dependent on the sample itself. So, I basically do this curve like I do basically depletion. I reduce the pressure, and I see how much of this asphaltenes is actually precipitated as a weight percent of the crude oil. So I'm actually simulating depletion kind of, which is a reduction of pressure. Or I can have solvent injection, like for example, I'm injecting CO2. I know CO2 will change the composition of the of the system. So I expect that asphaltenes will precipitate or not precipitate. First of all, why do asphaltenes precipitate when you inject CO2 or when you inject any kind of light solvent, like for example nitrogen or methane or this kind of stuff? Because you inject these solvents, you're making the system lighter. So if you make the system lighter, you expect that the asphaltenes will become less stable and tend to precipitate faster or more than the original system without a solvent. So for the experiments that you do in this case, you either measure the precipitate, how much you actually precipitate versus the solvent injection. Okay, when I inject 0.1 mole percent, I get this precipitate. When I inject 0.2, I get this much. When I inject, so on and so forth. Or you can check the change of the asphaltene onset pressure versus solvent injection, which is like, okay, I inject like 0.1 mole percent or 1 mole percent of solvent. Then I find that the onset pressure moved from the original one to another pressure, so that at EOR, for example, if you're injecting CO2, what is the onset pressure that will happen, for example, in the reservoir, what is the pressure that will induce precipitation, will start to induce precipitation of asphaltenes in the reservoir, and so that you can try to keep the pressure, injection pressure higher than this pressure, for example, as an application. So basically you have three categories of PVT experiments that you can do for asphaltene precipitation. You either do it for to check the conditions of precipitation. By conditions, I mean onset conditions like AOP, or you check the amount of precipitation, which is the precipitation weight percent versus either the pressure or the solvent. So price-wise, and let's talk prices, because as we started in the beginning, inhibition of the asphaltene or cleaning of asphaltene is actually costly. Actually, even the experiments of PVT in the lab is actually costly as well. So anything related to asphaltenes is actually attributed with the high prices. So till this greenish line here, this is a report from Geomark company indicating their own price list for experiments. These first kind of 10 rows or something like that, or 12 rows, represent the normal PVT two-phase experiments. So for example, you have CCA, constant composition expansion, you have differential liberation, 6 to 8 points, you have this price here, and so on and so forth. So for the entire package of the black oil PVT study, it's around $24,000 to get, to kind of completely characterize in terms of PVT the crude oil that you have. But if you want to add asphaltene experiments, you see that even for just 1 point of AOP, you can see that by near infrared, which is light, you can see that just 1 point costs like around 2,600. So imagine like you already done like 6 or 8 points for every experiment, and you have this price that you already are paying, and then you want to do like 3 or 4 points of AOP, you will actually pay like half of the price that you already paid. So this slide is just to highlight that the prices of PVT lab experiments related to asphaltene is actually very high. So if you can somehow reduce the experiments you need for the asphaltenes, quantification, or the asphaltenes, modeling and so on and so forth, as we're going to see later, this is actually very good. This will save you a lot of money. Like you depend more on the model more than the experiments. Of course, you need the experiments for the model to tune the model, but we're going to see how to reduce the dependence of the model on the experiment, so that you can reduce the number of experiments you can do, and hence reduce the price, because as you can see, it's very costly relative to the total price or even the individual experiment price of the normal two-phase PVT experiments. So what are the models of or the approaches of modeling asphaltenes or asphaltene precipitation? Again, I'm in the asphaltenes precipitation phase. I'm not talking about adsorption. I'm not talking about flocculation. I'm in the precipitation phase, if you remember. As we said, in the 2 points of view of the stability, it depends on which approach you're looking, how you're treating this instability. So if you colloidal, you have like example 2 models here, like the micellization theory or regular colloidal theory. But if you treat asphaltenes as solubles, like we talked about, you have a lot of or more models at least than the colloidal, and this is what I said when I said like the solubility approach is more common. The most common, even more common in the solubility models are the equation of state models, especially nowadays the statistical associating flow theory, which is the SAFT equation of state, especially the PC SAFT or the perturbed chain SAFT equation of state. This is because it is kind of the most recent equation of state out of these 3. This is the equation that Dr. Oliver Mullins followed, Dr. Lamiogwal followed, because it produces, by comparison, the most accurate or more accurate results than the other 2. However, this is what we're gonna see later in the model that I chose to model the asphaltenes, is that the cubic solid is actually very easy to not very easy, I mean easier than the other 2 to model asphaltenes. It doesn't need a heavy chemical background. Petroleum background is fine, and it is more common to compare. So even for the people who go for the SAFT, they already do the cubic solid just for the sake of comparison. So the cubic solid is common and easy and familiar among the modelers of asphaltene precipitation. This is why we're gonna go with the cubic solid model. So the assumptions of the cubic solid model: first of all, homogeneous asphaltenes behavior. This means that we treat asphaltenes as one entity, like one group. And of course, we know that asphaltenes are actually different species. So this assumption, of course, is just for the sake of modeling, but we know it's not true. There are no consideration for molecular interactions like aggregation, this asphaltene resin cross association, hydrogen bonding, reversible asphaltene precipitation. This means that, for example, if I reduce the pressure and the asphaltene precipitated, if I increase back the pressure again to what it was, it will redissolve in the crude oil. This case is not entirely true, because asphaltenes are asphaltene precipitation is a semi-irreversible process. Some of it will redissolve, but not all of it will redissolve. However, this kind of assumption was kind of remediated later in this model through this example of its remediation in these publications here. So this assumption is actually not anymore an assumption. The fourth one is that we do not consider the molecular geometry or structure. So, for example, if you have different molecules of asphaltenes, for us, it's the same. As long as the PVT experiments that, or the AOP, or the parameters that we're looking for is the same, we don't really care about the molecular structure or geometry of the asphaltenes. So there were 3, as you can see, that the cubic solid is actually started kind of relatively old, because again, as I said, it's easy to mathematically to deal with and thermodynamically to deal with. What I want to say here is that for this one, this is the one that I chose, which is the most recent one. It calculates the fugacity, and we're gonna know what is fugacity in a moment, based on an equation, not based on a correlation. And of course, we know the difference between a correlation and equation. A correlation is basically empirical. You fit a fugacity correlation based on the data or some data that you measure, and it's not global. It's not something solid that you can globalize on any crude oil. So this is why we chose the third one here, because this was an equation, as we're going to see later. And then here, this Qasi et al. Just drive the more general equation to include the effect of pressure and temperature. So most people, okay, say maybe not most. I mean, some people will, of course, know if you encounter this term, what is fugacity? You know what I'm talking about here. We still, what is equation of state? You know how we deal with this stuff. So so we're gonna step like few steps back and talk about equation of states in general, and just normal two-phase vapor liquid flash calculations, and then we're gonna move into how we transfer this two-phase flash calculation algorithm into three-phase, which has the Asphaltenes now, which is liquid, vapor, and solid. So we know, in the two-phase flash calculations, maybe this is, production 101 for some people, but for, just for, reminding myself and some of the others, basically you have a feed, you have the crude oil, and you flash it in a pressure temperature, how to say, condition. In this pressure temperature, you will have a separated vapor and liquid, right? So basically you have, this is the feed, F is the mass of the feed, V is the mass of the vapor, L is the mass of the liquid separated, ZI, YI, XI are the composition of the feed, composition of the vapor, composition of the liquid. For example, if you have the feed like nitrogen, CO2, H2S, C1, basically you have like we replace the mass by moles, and the composition becomes like the molar composition becomes like the number of moles of whatever nitrogen divided by the total number of moles of the feed. The same goes for the vapor, the same goes for the liquid. So we deal with this problem as a molar problem rather than a mass problem. Of course, you can deal it with mass, but generally we prefer to deal with mole. Also, like you can have a report or a crude oil analysis composition analysis that may end at C7 plus. The crude oil have C1, C2, C3, C4 till till basically almost infinity of C's, but during the composition analysis they stop at a certain plus fraction. So for example, you can stop at C7 plus, you can stop at C12 plus, whatever, and then when you flash it, you know that these components, some of it will go into the vapor phase and some of it will go to the liquid phase, and you basically is to know how much went into the vapor phase as number of moles and how much went to the liquid as number of moles, and also know the fraction of composition, like how much nitrogen went into the vapor phase, how much nitrogen went to the liquid phase, CO2, C1, C3, and so on. So, of course, we're talking about modeling. We cannot skip modeling without equations. So we're gonna state some equations from this slide and here on. You have, of course, mass-wise, mass balance, that the feed is equal to the vapor plus the liquid. Transforming it into the mole, language, it's number of moles in the feed equals to number of moles of vapor plus the liquid. And of course, for each component, that this is true as well. Like the nitrogen going into here, it has to equal the summation of the nitrogen went into the vapor plus the summation of the nitrogen went into the liquid, and so on. So this equation is also true for each composition, like for each component. I'm sorry, like I equal 1, I equal 2, the first component, second component, third component, and so on and so forth. For the sake of normalization, usually they treat the feed number of moles as 1, you know, as you have 1 mole entering, you know, this flash chamber, and then some references state that this is n dash, like because it's basically nv over n. It's like you divided this entire equation by n, but we just call it nv. Again, do not confuse with this one. It's just like I'm normalizing the number of vapors based on the number of vapors of the feed. You know, the number of moles in the vapor phase based on the number of moles of the feed. So NV is just a fraction, you know, and N liquid is just a fraction of the feed. You know? We're gonna define what's called the phase equilibrium constant, and of course, since I put phase, I have to put which phase. Here I'm gonna like it's vapor liquid phase, but we're just gonna say V because later we're gonna say S for the solid liquid. So this is why we put the V here. It's basically how much of the component went into the gas relative to how much of the component went into the liquid. It's not exactly like that because this is related to the number of liquid in the liquid, number of moles in the liquid phase, and this is related to the number of moles in the vapor phase. But you get the idea. It's like basically like let's say at least conceptually how much of the nitrogen in the gas to how much of the nitrogen in the liquid. From these two equations, the second red one and this Ki equilibrium constant definition, we can you know, mathematically derive or reach these two equations here, which is basically relates the composition fraction of the liquid to the of course the feed composition, which I should know, and the number of moles of vapor in the number of moles in the vapor phase. It can be also a number of moles in the liquid phase, but we know that this equation is true, and hence this is the one that came here. So it just can be one of them, either the vapor or the liquid. And of course, we know that the yi is just the multiplication of xi and ki. So again, we know that for the, let's go back here for a moment. We know that this yi is the composition of the vapor phase. If I sum the composition of the yi, it should give me 1 because it's basically, it will give me NV. So it's like Ni, N1 plus N2 plus N3 plus N4 divided by NV. This is the summation of yi. So I know that the summation of xi is 1. And I know that the summation of yi is 1 as well. So if I sum the entire, you know, composition of the liquid or the entire composition of the gas, I will get 1. And of course, the feed, I will get 1. And from these two, if I, you know, subtract this from this, I will reach to this equation, beautiful equation, which is kind of heavily outlined, as you can see, bordered in black, which is equal to 0. And this will be my objective function. So basically, this is the equation I want to reach. This is the, if I reach this state, if I sum all the composition, all the, you know, this equation here, and I reach 0, this means that everything in this equation is true. You know, so basically, if I know the composition, the equilibrium constant for each component, I can sum this, you know, Z1, K1 minus 1 over NV. This is, of course, one unknown. K1 V minus 1 plus 1, the same for 2, the same for 3. And I will assume and try to get the NV that when I put it in the equation, it will give me this objective function, which is 0. So basically, if I know the KIV, and I can just assume by trial and error, find the number of moles of the vapor phase that satisfies this objective function, to, of course, to an error, of course, probably I will not reach 0 as absolute 0. It will have to be something, you know, very small. And I can reach this by trial and error. So this is just the mass balance flash calculations some of you or many of you might already know about. The problem that I have is that the KIV, the equilibrium constant, if it is a single component system, it's a function of just the pressure and temperature. So for example, propane here, see this is pressure, this is temperature, and this is the K. You can see that I can get the K dependent on the pressure temperature, which I already should have known. I know the conditions I'm flashing my crude oil into. So if it's like that, then my problem is just been solved. I know this. I know for every component, I will just try to find the NV that satisfies this equation. But unfortunately, for a multi-component system, it's actually a function of composition as well. So what I mean by that is that, for example, propane, if you have propane and if you have liquid butane and pentane and you flash this system, the propane will drop more liquid than if it was by itself. It's like the butane and pentane is dragging some of the propane into the liquid, So this is what I mean by it depends on the composition. It depends on how much you actually have in the liquid and the vapor, So this poses a problem. This means that I have two unknowns and I have one equation. How I'm gonna solve this? It's based on just the mass balance. I cannot solve it. It's just one equation and two unknowns, or it's actually not two unknowns. It's actually n unknowns because I have Ki for every component that I don't know. And this is where the equation of state comes in. So basically, what is an equation of state? An equation of state describes the relationship between pressure, volume, and temperature with the states of the fluid, either vapor, liquid, or later we're going to see the solid equation of state. So there are many equation of states. These are the most or the two most common equation of states that we know as flash for flash calculations at least, and they are just extensions of van der Waals. If you're familiar with van der Waals equation of state, these are just continuation or extension of van der Waals equation. These A and B, of course, pressure, universal gas constant, temperature. This is molar volume. This is why you don't see N here. If you're familiar with PV equal nRT, this volume is basically the molar volume of the volume per 1 mole. And the A and B are parameters that depend on the equation of state itself and depends on the component in terms of critical temperature, critical pressure, critical volume, critical, these kind of. Basically, this is why the model is called cubic equation of state, because this is a cubic equation with respect to volume. You can see here, this is V squared. So if I multiplies by V cubed, I will see here V cubed, and it will be here. This equation reduces into a cubic equation of volume. So this is why it's called the cubic equation of state. This is just for that. The same goes for here. So this equation, if I want to reduce it, if I want to solve it, it transforms into solving it into what is called compressibility factor equation of state. It's still cubic, but they transform it from volume in terms of volume to in terms of Z. I don't want to get into a lot of details in this step of this transformation. Basically, the Z, like just briefly, is almost like 1 over V. So treat this Z as 1 over the molar volume. And again, what is A, what is V? It's function of the small a, the big, like the capital A is function of the small a, function of the small b, capital A is function of the small b, and the critical pressure and temperature for each component. Okay, so what do I do if I have multiple systems? Then there is a mixing rule for this A and B that I'm gonna shed the light later. So you have A, for example, mixture, and B, mixture. The idea is that this equation you have two of, one for the vapor, one for the liquid. So basically you solve the one for the vapor and you take the maximum real root, the minimum real root for the vapor as the Z vapor, and you take the maximum real root as the liquid. And why do I do that? Because if you remember, as I told you, Z is, I just won't get much detail. Z is basically like treated as one over volume. We know that the volume of the gas is high, so the Z of the vapor, volume of the vapor is high, so the Z of the vapor is low. So this is why we take the minimum real root as the Z, and vice versa for the liquid. Like the volume of the liquid is low, so the Z of the liquid should be high. So this is the maximum real root of the of this equation. So we have two equations, one for the liquid, one for the vapor. A and B are the mixture of the components of the system in the vapor or the liquid, depends on the equation I'm solving, and they are functions again of fixing rules of the small a and the small b, and the critical temperature and pressure of all the components in the vapor or all the components in the liquid. So after getting this, you solve this one long nasty equation. This is actually the equation of state that you find the term fugacity. So remember, we were talking about fugacity, and some people were saying, what is fugacity? Fugacity is basically a term that describes energy. You know, it's basically a term, like, if I want to properly define it, is the energy, like if you want to kind of Wikipedia define it is basically the energy of getting from one compartment to the other compartment, something like this. So basically it's like treated as the energy of this component, the vapor phase. And of course we have the same equation for the liquid with substituting each vapor subscript with L subscript, you know, and again you have the for the V, you have the each of the V component capacity of, and you do this for all the components that you have. And then of course, since I have like n components, I have to have an objective function. So basically I sum, I know that at equilibrium, the fugacity of liquid should be equal to the fugacity of vapor, because the component will separate into the liquid and the vapor, so that the energy in the vapor is the same as the energy as the liquid. Because if there is a difference, let's say the energy in the vapor was lower, then the material or the compound will prefer to stay in the lower energy phase. It doesn't want to have this higher energy. So at equilibrium, its energy in the liquid should equal its energy in the vapor. So when you know -1 and you summate and you do the square thing to cancel, you know, the negative and positive, you should reach this 10 power negative 13, which is very, very close to 0. And you treat this as objective function. So now I know that I want to get the system, first of all, I want to get the correct molar volume, number of moles of the vapor to get to that state of getting yi and xi. And after I get y and xi, I get to this stage, I calculate the equation for the vapor, I calculate the equation for the liquid, I get the Z vapor and Z liquid, I substitute here, I get the fugacity of each component in the vapor phase and the liquid phase. I want to reach this stage. Okay, what happens if I don't reach this stage, if this condition is not met? Then I substitute the amount that I did not know initially as a function of this ratio that I already calculated. So basically, the equation of state calculations are two loops inside each other. One for the mass balance, you know, I want trial and error to get the correct number of moles in the vapor phase, and xi and yi, you know, and then one for the equilibrium constant, because I don't know the equilibrium constant. So I will just start with an initial value and get the NV, get the yi and xi, get the correct Z vapor and Z liquid, not the correct, get the Z vapor and Z liquid for this iteration, get the fugacity of vapor and liquid for each component, check my objective function. If it's not met, then
I substitute with the new value of the equilibrium constant by the values of the Fugacity. And I do these two loops all over till I reach both objective functions to be satisfied. So basically, this is why the equation state comes as an extra step for more than the normal mass balance flash calculations. Of course, after I finish this, my output is going to be, okay, how much of the feed I got in the vapor, how much of the feed I got in the liquid, and the fractions of each component in the liquid and vapor phases, respectively. Also, these kind of calculations are very useful if you want to optimize conditions. For example, if you want to optimize separator conditions, like you want to, when you build a separator, you want to put it at the pressure and temperature that will maximize the liquid dropout. So you want to maximize this in liquid. So you basically do this entire algorithm for different pressures and temperatures and find out which one will give you the maximum in liquid, because this will be the maximum mass of liquid that you're gonna get after doing the flash calculations. So how does the experiments come into this algorithm? This is what we call the tuning step. There are a lot of parameters that you can tune in. The parameters that I'm concerned with that we used in this model later, as I'm going to show, is related to what's called binary interaction coefficient. So if you remember, I told you in the calculation of Z, for example, for the vapor, and the calculation of Fugacity, you have the mixture of vapor, which is, this equation depends on the Yi and Yj, and the what's called the Aij between I and J component. And this parameter here is basically calculated by this equation. We call this parameter here, of course, Ai and Aj, as I told you, A, just like A1, for example, is A small multiplies A1 small multiplies by pressure R square and temperature. So I have the A for each component, The problem is with this parameter. This parameter is called binary interaction coefficient. It basically describes how different components interact with each other. So if the binary interaction coefficient is high between component 1 and component 2, this means that component 1 and component 2 are not much compatible, like, for example, asphaltenes and methane, for example. Asphaltenes and methane have high omega because they just are kind of far from each other in the span of the composition, How we get this parameter is basically a function of the critical volume of each component, which I know, but it's to the power of something called the A parameter of the tuning exponent parameter. So basically, this is the parameter that I tune in. So, for example, I have measured saturation pressures or constant composition expansion experiments or whatever experiments that I have in the PVT two-phase experiments. I have the measured value of the pressure and temperature. For example, for the saturation pressure, I highlighted in green because this is the one we used in the model. Later in the Asphaltene model, I mean. And then I have this one. So I do these calculations to try to reach the same pressure that will give me, the exact flash calculations at this measured pressure. And then this will correspond to the correct E or tuning parameter. So this is an example of what I'm tuning. Tuning is like I'm changing the parameter to match a parameter to match an experiment that I measured already. So now we understand the two-phase and the question, say what does Fugacity mean? What does this kind of stuff mean? Let's take it back to the asphaltenes. Okay, now I have a third phase, which is the solid phase. How are we gonna treat this? Now I have the feed, but it's again 3 outputs. I have the vapor, I have the liquid, and I have the solid. So instead of having one mass balance objective function, and I now have 2 mass balances because I have sigma y minus sigma x, which is this equation, and I have sigma s is the solid, composition minus x, which is the this equation here. So I have two objective functions, so it gets even more complicated. And of course, I have the equilibrium constant defined as y over x, or for the solid as s over x. So okay, what shall we do to simplify these kind of equations, or the you know, these kind of mass balance equations? So we're going to state two of the assumptions that we followed in the modeling of the third phase, which is the asphaltenes. Is that okay? I now have three phases. The vapor, I have from 1, 2, 3 till the n-1. So basically, I am assuming that the vapor phase does not contain any asphaltenes, because it doesn't make sense for the asphaltene as the very heavy component to be in a vapor phase. That's you need to have, you know, like a very extreme conditions, you know, to get to this stage. So basically, we just assume that I don't have any asphaltenes. So y asphaltenes basically is equal to 0. Then I have the liquid, which I have everything in the liquid, and I have the solids. But for the solid, I'm gonna assume it only contains the asphaltenes. So there are no other solid constituents other than the asphaltenes I'm studying, you know. So basically, I'm not modeling waxes. I'm not modeling waxes and asphaltenes. I'm not, you know, these kinds of. I'm only interested, or not interested. I'm only assuming that the solid that is happening, or, you know, precipitating from the liquid is the asphaltenes. So this, in terms of, you know, notations, this means that the SI for any component is 0, because I don't have any component other than the asphaltenes, and the asphaltenes is 1 basically, because it's all the number of moles of the asphaltenes is basically the number of moles of the solid phase. So I have these kind of equations here, and this will help me during the three-phase flash calculations, as we're going to see later. So this is just an assumption for the assumptions for simplifying the k and the, you know, the x and the y for the asphaltenes. What about fugacity? We know that in order to complete the algorithm, we should have something to calculate the fugacity of solid. We know that the Pring-Robinson or SRK equation of states only calculate liquid or vapor equation of states. So what shall we do about it? Here comes the solid model, and this is why the entire model is called cubic equation of states solid model, because it's the integration between cubic equation of states and solid model. So basically, you have this equation. This equation is basically a thermodynamic equation of how a solid is how to say is behaving from one pressure and temperature condition to the other. Okay, so basically we have the fugacity of a solid at any pressure and temperature equal to a reference fugacity plus the molar volume of this should be solid, but we know that the asphaltenes is basically the solid. So basically the subscript A and S are interchangeable. The S is the A and the A is the S. So this is the molar volume of asphaltenes. And then this is the pressure and temperature that you want to get the fugacity in. This is the reference pressure and temperature that you have the reference fugacity in. And this is these parameters are thermodynamic parameters like enthalpy, isobaric heat capacity, fusion, the subscript fusion like here and here. So this is fusion temperature, for example. So I have an equation that correlates solid to solid. Okay, again, I cannot operate with this. I have to relate solid to liquid because I have the K for solid to liquid, you know. So before moving into that, this equation reduces to this equation if the temperature is the same. So basically, if you want to test, like if you just reduce the pressure or increase the pressure or change the pressure in general, keeping the temperature constant, you will see that this term will vanish, this term will vanish, and you will have, you know, some mathematical stuff that you will see that all the thermodynamic parameters basically vanish. So you will have just this equation here. This is the isothermal condition. So we just put, I remember what the question that I just put a pin on, which is how to relate the solid to liquid. I'm still, there is a pin on that. So in terms of testing, now I know what I'm gonna do. I know that the objective check function that I'm gonna check, okay, I can get the liquid fugacity from Ping-Robinson of asphaltenes, and I can get the solid fugacity now. Like regardless, of course, I have to have this and this and this, but just imagine that I have this value now, and then I'm gonna check which is bigger than which or equal to which. If I have that the fugacity of solid is bigger, this means that the energy of solid or of asphaltene in the solid phase is going to be bigger, so it will prefer to stay in the liquid phase. So this will mean that there is no precipitation. And then if I have the fugacity of asphaltenes is equal, then I just check the time. I don't know if I surpassed the time. I took some time in the beginning. I'm sorry. I'll try to be as brief as possible. Then if it's equal, then it's about to precipitate, which is the onset conditions that we know. And if it's bigger, then there is a precipitation because there is less energy in the solid phase. How to get this reference? This is the answer to the pin question that I just. How to relate this to the liquid? Basically, it's basically in this step here. So in order to get this here, which is the solid fugacity, I will just have to find the condition that I know that the solid fugacity is equal to the liquid fugacity. And the liquid fugacity I can get from the Ping-Robinson or the SRK model. So basically, I have to have one reference condition. If I have AOP, then the AOP, we know that the AOP is the onset condition. So I will just calculate the fugacity of liquid at the onset condition and take it as the liquid at the solid fugacity because they are equal. I know that. But if I have like these experiments, like precipitate versus pressure, I don't have the AOP, so I have to extrapolate the precipitates to zero precipitate, so that okay, at zero precipitate I know I'm about to precipitate, so this is kind of a virtual AOP I can get. I am short in time, so I will just skip this. This is just how you treat the composition. So you have a composition like what we saw here. You transform this composition to this composition. This is the composition that you calculate. You split the flux fraction into 13, C 8, 9, 10, till you reach a satisfying plus fraction that you think this is the asphaltene. This depends on the molecular weight that you're going to reach at the end. And also you lump components. So you group components that you think they have similar properties to each other. The reason we do this is, first of all, of course, to reach the asphaltene component, because the asphaltene component, we have to be a molecular weight close enough to what we know about asphaltenes. And of course, not to have like 30 components that you want to calculate, because this, if you calculate for 30 components, practically in a simulator, for example, in a compositional simulator, you take a lot of time. So you want to minimize the number of components as much as you can, so that practically and time-wise, you save time of calculations. I'm going to skip this for now. So now you know that we split and you lump the properties and stuff. And for the tuning, you basically tune. We know that for the green value, it follows this equation, which has this tuning parameter. But for the asphaltenes, it's basically these values are the values that you tune. And you tune for the molar volume of asphaltenes as well. And the experiments that you use for tuning is the PVT experiments for asphaltenes, which is the AOP, precipitate versus pressure, and so on and so forth. Now comes the part that I did my humble work in, which is what were the drawbacks of this model. This model was, as you saw, it has thermodynamic parameters. So how are we gonna get this thermodynamic parameters? So what they did before is that they had multiple onset parameters, so that they fit this equation. Like for example, if you have 2 points or 3 points, you can fit these equations to obtain either the delta CP. Of course, if you have 2 points, you can only get one of them. So because you have one as a reference already, a given, to get this. If you have 2 points, you can get both of them. So basically, you need more experiments, and we know that more experiments means more money. So basically, you need more experiments to get these. And also, one drawback was that in case of solvents, you need to have also more experiments, because if you do a solvent injection, you're basically changing the entire composition. So you're basically the fugacity of the reference is no longer the same. It's not onset at the same pressure and temperature because you change the composition. So you need another AOP for the new composition with the solvent. And then if you add more solvent, you need another AOP for the, so on and so forth. So basically these two indicate that you need a lot of experiments to work out this model, So the modification that we did in terms of my work is that instead of getting the parameters from experiments, we just found that there are correlations for them for waxes and aromatics, and the general correlation for both waxes and aromatics. So we're gonna treat asphaltenes as waxes. I know it's not optimum, but we just see, okay, I'm saving now the experiments I need to get this TF and delta H and delta CP. We're just gonna see if it was behaving thermodynamically as waxes, if it was behaving thermodynamically as aromatics, And then we came out with this, okay, it's not waxes and it's not aromatics. Maybe it's something in the middle, something average in between, So instead of getting either waxes or aromatics, we came up with this averaging techniques that basically average the how much of it is waxes and how much of it is aromatics based on the Sera fractions and the wax report, if it is reported in the PVT report, So basically you just either take the saturates as the one for the waxes, because the waxes we know it's saturates, and the aromatics we take everything else, or you take relative to each other, not relative to the entire, Or you put, if you have the waxes reported, you just take the waxes on the asphaltenes and the asphaltenes, So you basically have 3 different averages, and we want to check which average should match more. Again, this saves me the extra experiments to get the fusion temperature and or the enthalpy of fusion. For the solvent drawback, we found that the AOP is actually a linear function of the how much you're injecting solvent. So this means that if it is a linear function, I have for no solvent, I have AOP. And I have for 1% solvent, I have AOP. But if I do 2% solvent, I don't have to measure the AOP. I can just extrapolate the line to get the AOP if I have 2% solvent or 3%. So I saved the money of doing the extra measurement of AOP for the extra mole percent solvent. So basically the procedures, you have the composition, the plus fraction properties, the Sera fractions for the averaging, and of course for the asphaltene, the saturation pressures and temperature for the tuning, the experimental data for the tuning of the model of the asphaltenes and so on, the conditions, which is the pressure and temperature that you want to flash in. This experimental data can be AOP, can be precipitate versus pressure, plus the temperature of the experiment, and so on, as the PVT experiments that we explained. Then you do the characterization, which is the splitting and the lumping that we talked about. You tune it, which is find the E and the sigma and the VA that we talked about. You do the calculations of whatever conditions that you want to flash, and then you get the output, which is the entire envelope, or how much of it precipitates versus pressure, and so on and so forth. Let's go into the samples, how we tested these modifications into the model, the oil samples that we have. We have like 14, we tested on 14 oil samples. This is when I told you guys that even if we have very low amount of asphaltenes, there's still precipitation tendency of this specific crude oil or sample that we needed to do PVT experiments. We had 5 AOP, we had 5 precipitate versus pressure, we have 10 solvent. We characterized some of the result as the mean absolute percentage error. It's basically like how much predicted minus the actual value, this kind of calculation. And we can see here that this graph here is the envelopes using the different thermodynamic. Either I do the waxes, it's not waxes, I'm using the waxes thermodynamics, correlations. Either I do the aromatics, either I do averages, as you can see here. You can see that the envelope, if you remember the shape of the envelope from the introduction, it should close on the vapor liquid, but for the waxes, it's not stable. It's kind of inconsistent. It goes back. It does not close on the vapor liquid. If I put the points, you will see that the average, even though I just used one reference point, the averages already give me close values to the points that I would have needed to use the model if I didn't do this kind of modification. The same goes for the sample 2. Sample 2, I had the waxes, so this is why the third average appeared in. And you can see that maybe one says that, okay, the aromatics is actually closer, but by the numbers, you will see that the average is actually closer than the aromatics because it's closer to this point here. This is the third sample, the same. The fourth sample was kind of odd. So you had this, like the OEP did not decrease with temperature as usual. It increased, then decreased. This is why the waxes were kind of closer in terms of the upper envelope, but the lower envelope was unstable for the waxes. So because again of the inconsistency that I'm saying. This is the mean absolute percentage error for the samples that we show. You see that the averages has the least error of all. And we know that I already saved the money and time for the experiments that I would have needed to get the thermodynamic parameters. And for the sample 4, we saw that the waxes were already close because it was an odd sample. For the second type of experiments, which is how much precipitated versus pressure, I compared my model to a composition, to a software called PVT Pro. These are the features comparisons between my model or our model and the PVT Pro. What I want to highlight here is that two things. First of all, I only deal with saturation pressure. This is why I don't deal. I mean, when we programmed the model, we did not program DL or CCE or whatever. And also the predictability, as you will see later, I can predict at any temperature because from the thermodynamics, I can have any P and T. But for the PVT Pro, if you have the precipitate versus pressure experiment, only this, you can only predict at the temperature that you put the experiment in. So this is the sample, this is PVT Pro, this is my model, this is the experiments, the green dots. This, I apologize for the kind of crappy plot because I could not find the actual data when I was preparing the presentation. So I put it from, I took it as a picture. So this is why it's kind of not so good. This is the model PVT Pro. This is the sample and the PVT Pro model in the smaller image here. I want to highlight here is that when you do tuning on a precipitate versus pressure, it's a depletion experiment. It's one temperature, so the thermodynamics is not there. This is why you can here see the PVT model, PVT Pro model. But if you want to predict at a different temperature, you cannot using the software PVT Pro. This is why you have here because the PVT Pro does not have these parameters. You know, but for my case, I already average it, so I have these parameters. So you can see that the averages are closer to the values. For the sample 4, you can see that the waxes are closer for the both temperature, and this agrees with the phase envelope analysis of the same sample because it was an odd sample. The waxes actually passed by the more or closer to the points than the aromatics. This is why you can see here is closer to the points than the aromatics. For the AOP, this is the kind of empirical proof that any AOP for any sample, this is one sample, for example, at 3 temperatures, as you increase the solvent percent, you actually get a linear relation between measured AOP and the solvent percent. And this goes for different samples as well, as you can see here. Irrelevant on the sample, irrelevant of the solvent, it's always linear, at least for the samples that I did the relation with. And this is the model experiment. You can see that I can predict either for different solvent percent, as well as the upper AOP. If I have just one reference, I can get the rest if I use the aromatics or the waxes. I should have done the averages here. You can see that it will generally pass closer to the in-between points. And you can see that the wax is still inconsistent, it's still increasing like this. It does not
flows on the vapor liquid diagram. For the precipitate versus solvent, like, okay, how much I inject versus how much I precipitate, this is the most complex experiment because I have 4 parameters changing: pressure, temperature, composition, and the amount of precipitate that is forming. This is the behavior of the model after tuning. This is the behavior of the same sample but with different solvent, which is C1 over C2 equal 80/20. So the conclusions for the model is like a modified cubic Ping-Robinson solid model was developed. We used 2 sets of thermodynamic correlations instead of trying to fitting it with extra experiments. 3 averages were introduced as well. A linear function was proposed. However, we still need an additional function for the precipitate versus solvent. The model handled all PVT experiments as related to asphaltene, I mean, and the model was tested or validated by 14 oil samples. And of course, we compared for commercial software with the precipitation experiments. We found that the average number 3, if you have the waxes reported, this is the best average in terms of thermodynamics to save you the experiments and get you closer to the points of experiments as possible. And if you don't have the waxes, we recommend the average number 1, which is the S/ARA average. And the new approach, as you saw, it reduces the dependence because I don't need extra experiments to fit the thermodynamics, and it produces closer reliability because the averages gets you closer to the points. The recommendations is that you test. We test this kind of thermodynamic on more samples to consolidate, or globalize the concept. And we can use this kind of concept, aromatics correlations or waxes correlation, in other models because it's not just the cubic model that has the thermodynamic parameters. Also, the cubic plus association models have thermodynamic parameters. So we can test this kind of application in it. This work, of course, was done in the Cairo University under the supervision of Dr. Helmi Sayouh and Dr. Ahmed Al-Bambi. So thanks to both of them. And of course, I want to thank Dr. Ahmed Al-Garhi and Jumana for giving me this opportunity to present. And I'm sorry I took a lot of time. Time kind of stole me. So I hope I cannot say I was a light presenter, but I hope I delivered the message that I wanted to deliver. And thank you.
Dr. Aktham, thank you very much for the great presentation. I believe we received just one question. Please explain asphaltene property with respect to wettability alteration.
Sure. Let me go here. I think I know where he was talking about. I think it was this slide. So basically, asphaltenes, as we saw, it's polar. Okay, so if you, or as we know, it's polar. So if you have a polar or especially calcite surface like a calcite reservoir, and this is polar and it has acidic groups like negative groups, it will adhere to this polar calcite surface. So if it adheres, then imagine like you have a surface and it's attached to aromatics and naphthenic groups and naphthenic rings and stuff. This will make the surface more oil wet because it's it will attract the oil due to this hydrophobic chains than the water. So this is why it makes the surface more oil wet due to asphaltene absorption. I hope I answered the question. And then, yeah.
Dr. Aktham, thank you very much. It was a great pleasure having you
today. Thank you. I'm sorry to take much time.
It's okay. Guys, as normal, this presentation already recorded and it will be uploaded to PyroPetro. So please, if you want to watch it again, if you want to share it with friends, you can get it from PyroPetro YouTube channel. One more time, thank you, Dr. Aktham, for the great presentation, and enjoy your rest of the day.